There you go. Okay, so good morning again. Welcome to APNIC e-learning web class. This topic that we're going to cover for this morning is all about IPv6. So it's an overview of what is IPv6, what are the why do we need IPv6 in the first place, what are the different differences between IPv4 and IPv6. We'll look into the packet headers. We will look into some of the basic functionalities, basic features of IPv6. All of that we'll try and cover for this 1 hour session. This class, it will run for 1 hour, and so we will allot about 45-50 minutes for the class proper. If you have questions, please feel free to ask them all throughout the class. Just a few housekeeping things before we begin. Today is July 3rd of 2013. It's 10:30 in the morning from where I'm broadcasting this, which is in Brisbane in Australia. Now, to introduce myself first, my name is Cheryl Hermoso. I'll be the training officer for this morning and all throughout the sessions for this afternoon as well. If you have registered for that, I'll be covering all the IPv6 topics. We have 3 for the day. This is the first one, V6 overview. We also have IPv6 addressing and subnetting later on, and IPv4 to IPv6 transition at 2:30 in the afternoon. Now, as I've said, my name is Cheryl Hermoso. I work as a training officer with APNIC for the past 2 years now. And as part of the training team, we do deliver face-to-face trainings to our members of the internet community all around the Asia-Pacific region. So the topics that we cover are basically the ones that you can see on the board here: network security, IPv6, internet resource management, DNS, and DNS security. All of those topics we cover, and to let's say if most participants can't get to a face-to-face training, we cover e-learning type of courses such as this every Wednesday, and that runs for 1 hour. Now, at the end of the class, there will be a brief survey, and so I would like to encourage you to answer that at the end. It's just like a feedback form to know whether we've accomplished our goal of extending information about IPv6 to you, and also if you have other suggestions perhaps of other topics that you want to be covered in the future e-learning courses. So with that, I'd like to go through our topic, IPv6. So what we'll be covering, what is IPv6? We'll look at some protocol background. We'll look at the different functional improvements, different features of IPv6. We'll look at the addressing models. There are 3 types, so we'll know what types are, let's say, will be used for different purposes. We have unicast, multicast, and anycast. All of that, we'll try to cover them. We'll look at the different protocol headers. We'll compare IPv4 and IPv6 headers, the different fields, and what has changed from v4 to v6. We'll look at interface ID. This covers the addressing. So basically, it's divided into 2 parts. You have the interface ID and the rest of the IPv6 address. So what is an interface ID? What are the different types of IPv6 addresses as well? Just a brief overview of that towards the end. And then we'll do address distribution. So how do we distribute IPv6 addresses? What is the let's say, is there a hierarchy that should be followed? Are there protocols that has to be followed? All of that we'll try to look into. And we'd like to welcome another participant, Karthik. Hopefully I pronounced your name correctly. Thank you very much for joining us. We're having some issues with other participants, so we'll try and hopefully some more will be attending really shortly. So that's what we want to cover for this morning. I hope that is really what you are up to for this morning. If you have questions that are outside of that coverage, we will try and discuss them as well if we have enough time. Otherwise, again, this is an introductory course. We will go from the very basics. We'll look at, let's say, protocols. What is IPv6 protocol? What is an internet protocol? That's what we're starting with. So in this slide, what exactly is IPv6? Before we can answer that question, we need to know what is a protocol. So I'm not sure what your background are, but I will start from the very beginning, as I've said. So to answer the question, what is a protocol? I'm pretty sure some of you have that in mind already, but just to define, protocols basically define the rules for data communication. It's a means of establishing like a common language that is to be used by different devices on the internet. Everybody that connects to the network basically so that they will have meaningful communication, so that it will be possible for them to understand each other. So protocols achieve this by defining, say, the nature of, say, the information that has to be communicated between them, and what actions has to be taken when this set of, let's say, set of communications process, or the numbers or the ones and zeros receive from the upper layer. So how they will interpret that and how it will be encapsulated to be transmitted to the next layer. So we will cover that basically. So we have the protocol stack group. So it does these actions, so making all the entire data communications process into different layers. So when we talk about Internet protocol, that is one layer of the Internet protocol stack, basically the TCP/IP protocol stack, that is responsible for the data delivery, and also from, let's say, when you're delivering packets from a source address to destination address. That's what we do. So IP basically stands for the Internet protocol, and TCP/IP is the main language that we use on the Internet. So with that, what is IPv6 then? So IPv6 is just a version of IP. We have IPv4 as our current version, right? So IPv6 is the newer version of IP protocol. And I wouldn't go as far as saying that it is new, because if you look into history, it has been here for a really long time. We have on the next slide a brief rundown of what has happened on the Internet scale. So when did it begin? Actually, it's been around more than, say, around 15 years, I would say, because it started out in 1990s. We came up with IPv6 because there is a need for us to come up with a new protocol, given that we saw a need for it. Why? Because we were running out of IPv4 addresses. That is the main compelling reason for having IPv6. Now, some people would tend to ask me, how come we jumped from IPv4 to IPv6? What is the reason for that? Now, there was actually an IPv5. It's called an Internet Stream Protocol. So it was an experimental protocol. It's not something that has been implemented by manufacturers onto actual devices that are shipped out and used commercially. So again, it's a commercial, it's an experimental protocol, and it's never been used commercially. Now IPv6, if you look at some of the older documents when they're discussing about the proposals and then the actual protocols, you will see it called as IPNG. So IPNG stands for the IP Next Generation. IPv6 was actually named as IPNG before it was named as IPv6. Once they have the final standard, that's when it's called IPv6. So earlier documents and proposals, or anything that you read on mailing lists in the early days, all talk about the IP Next Generation. So it's all about the same things. The specifications and all that have somewhat changed. It's based on what everyone in the community think and agreed upon, but basically IPNG is IPv6 during its experimental or during its development stage. Now, this is just a diagram, an illustration of the TCP/IP protocol suite. So basically what I want to show you here is that when we talk about the changes between v4 and v6, we talk about one specific layer, and that is this layer, right? This layer, basically, this specific protocol. So most of the changes that happened here. Of course, the protocols on top of that, more specifically in the application layer, will have to follow suit. Like they may have changes here and there when it comes to how they deal with the IP addressing and all that. But essentially, the main changes, the main differences that we will find, all will be in this layer. Okay, so as you can see, processes are modularized. So a protocol layer defines basically what set of operations are implemented on that particular phase or that particular layer. So in our case, IP, everything that has to do with IPv6 and IPv4 are in the in this layer. Okay, Now let's look at some background. Basically, what happened? Why do we need IPv6? Okay. Now, the internet began in 1970s. I think we can safely assume that. It started out in the late 1960s, but it actually started propagating, started delivering, connecting different nodes in the US, and then later on, academic institutions, government institutions as well, and not-for-profit organizations started converging and connecting to that same network called ARPANET. Okay, so it's just grew bigger and bigger. So it just started in the US, expanded onto, say, Europe, and then expanded onto Asia, in North America, South America, and now even Africa. So we did not foresee that growth. In 1970s, when they came up with the TCP/IP protocol, if you are familiar with Vint Cerf and Bob Kahn, the TCP/IP protocol that they publish essentially just list down a range of addresses that can be used, which is 32 bits. That's what we know as IPv4. Now, in the early 1990s, there actually was a shortage of addresses. This was the time when we are still using classful addressing. So how are we distributing IP addresses that time? Well, they have a lot of addresses. That's 32, right? 32 bits in an IPv4 address. So the entire IPv4 address pool is actually 2 raised to 32, which is around 4.3 billion addresses. However, the way it is being distributed was classful, if you're familiar with Class A, Class B, and Class C. So during that time, they thought that if we continue doing this, so the first wake-up call was sent out by a guy named Zelensky in IETF. He sent out an email onto the mailing list with an actual computation of, say, if we are distributing this much in a year, we will have provided or given out all of the IPv4 addresses in around 1994 to 1996, in that span of time, which at that time will just be around 5-6 years from the time they sent out that email. So it was from that day they started talking about what are we gonna do, what will be our plans. So as in any problem, there were two solutions. One is a short-term solution and the other one is a longer-term solution. The short-term solution that they thought of was to get rid of classful addressing, and so this time they started using classless addressing or variable length subnet masking as well, or CIDR. So all of these were implemented. Basically, we're not reliant on the classful addressing anymore. So if you want actual, say, addresses that are more than 512 but less than 65,536, you don't automatically get a Class B. You get somewhere that's in between that. Probably you'll get a /23 or a /22 for all we know. So basically that is the short-term solution. Now the long-term solution that they come up with is to implement or to come up with another protocol that can provide more addresses, and that is when we came up with IPv6. All right, so IPv6 addresses the main issue of addresses, the number of addresses. We don't have enough of that in IPv4, and so they decided to create a new protocol, which is IPv6, that will address that problem. So in December 1994, that was when they started out, say, asking people around, asking for proposals from the community of what should this IP next generation protocol have. Should it have, say, 64 bits of addresses? Should it have 128 bits? So there were many protocols. There were many proposals that were sent out. Okay, most of these proposals vary. Say the PIP protocol, catnip protocol, all of that have different specifications. So the reason we're using 128 bits now, it's not exactly rocket science. It's not like, well, this is the most, based on some computation scientifically, this is what we should have. It's actually more of an agreement between and among the community, because the proposals mention different things. One of them said we should have 64 bits, but there was worry about that before, because say what happens if we came up with the same problem? Let's say after just about 10 years we run into the same issue. Are we going to create another protocol by then? So that was the main problem with 64 bits. And so they thought, what about 128 bits? Well, that seems like a really, really huge number, but yeah, maybe we can do that. Another proposal was to use variable lengths. So basically, we'll start off with perhaps 64 bits, and then eventually we can like increase that as we need them. So in the end, based on the community's consensus, they came up with 128-bit address as IPv6. Now, the first versions of the IPv6 address specification was came out in 1995, and it was standardized in 1998 as RFC 2460. So any questions with that? So basically, that's how we came up with IPv6. Now, the another issue there is, say, we have like some experience with IPv4 now. What are we going to do with the next protocol with IPv6? Are we going to imitate everything that we've done in IPv4, but just with an increased number of addresses, or should we improve it? So when they came up with the TCP/IP protocol, you know that we have very little knowledge about how we are going to use the internet, how we're going to use the network. And the way we use the network has changed immensely from the early days where we just sent out texts type of messages, very small 64 kilobyte type of messages. But nowadays we use streaming. We send out big chunks of information over the internet. So the way we use the internet has changed, and so they thought that, well, we should improve what we already have right now. So let's look at some of the improvements of IPv4. What are some of the features that we have introduced in IPv6? Now, the main compelling reason with IPv6, as I've said, is pretty much this. Okay, others are just an additional. But the main compelling reason why we have IPv6 is essentially because we don't have enough IPv4 addresses. IPv4 is 4 billion addresses. IPv6 is 128 bits, which is, when you look at the addresses, okay, or the number of bits in an IPv6 address compared to IPv4, it's 4 times bigger. But it doesn't mean that the actual address space is actually just 4 times bigger. It is more than that. It's heaps more than that, because this is exponential. So the number of addressable space or addressable devices that you can think of with IPv6 is around this. It's 3.4 billion addresses. That is a lot. However, we did not think, when in the early days with IPv4, we did not think that 4.3 billion addresses is just enough, or it's not enough. Actually, we thought that it's also a really big number. But we are in the same phase with IPv6 now. We think that 3.4 billion addresses may be too much, but who knows? Maybe in 10 years' time, in 20 years' time, we will also like have used up most of these addresses. Okay, but for now, you can see that's a lot of numbers. That's 5 times 10 to the 28 addresses per person, if you think about allowing or giving IPv6 to one person. We have around 7 billion people in the planet right now, and if you give one for each, that is 5 times 10 to the 28. Now, as I've said, aside from that addresses, we have improved IPv6. We have introduced a lot of new features, and we'll look at that in this next slide. So what are some of the functional improvements? Of course, the very first one is the increase from 32-bit range to 128-bit range of address space. We already know that. We have established that in the previous slide, and I think you are all very familiar with IPv6 addresses by now, the address space at least. Now, what are some of the other improvements? Here, we have stateless auto configuration. Now, this is something new with IPv6, okay? So basically, what is this? Now, if you connect your computers onto a network, basically what do you do? In an IPv4 network, either you assign a manual IP address onto that machine, or in most cases right now, we have DHCP servers. These are third-party servers or devices that are able to provide DHCP addresses to computers, to devices using a DHCP service. Now, with IPv6, we don't necessarily need that third party, or we don't also need to have to apply IPv6 address manually. This is done automatically. So once you configure or once you enable IPv6 onto your machines, you can automatically have an IP address. Okay, and through this IP address called the link local address, your machine will be able to communicate with other machines that are IPv6 enabled within the network and be able to send and receive messages from that. That is stateless auto configuration. The idea behind that is you don't have to worry, you don't have to ask someone else, let's say a network admin, to configure your machine for your machine, but you can automatically have connectivity once you essentially connect to the network via wireless or via wired cables. Okay, so that's a really good thing for IPv6. Next one is the fixed header size. In the next slide, we will look into the packet headers. We'll look at the differences between them. But essentially, what we mean by this is when we say fixed header size, we don't essentially have to worry about computing the size of the packet every time it passes through a router. Now, it's also 64-bit header line, which is the same as most devices now. So you'll have better router and switching performance. So that is a pretty good thing with IPv6. And compared to IPv4, which has 20 bytes of headers, but it is variable. So every time a packet comes into a router or a switch, it has the actual size has to be computed, okay, before it's sent out forward to other devices, which added to the load of the switch or the router. And so if you have older legacy systems, then it might not be good enough for that. Doesn't have hop by hop segmentation. Now, when you send out, say, a packet, a message, say from, let's say, router A going to router B, or let's say router D. Router A to router D, it has to pass through, let's say, router B and router C. Okay, so 4 hops. Router A goes to router B, C, and D. D is the final destination. Now, normally, a router will set what we call an MTU, or the maximum transmission unit. Now, this is the maximum size of a packet that can be passed through to their network, basically. So, what do we mean by path MTU discovery in V6? In V4, when you send out a packet that is larger than the MTU size, okay, it will be dropped, and the sender, say in this case router A, will have to fragment his packets and say split it into 2 and then send it one by one. Now in IPv6, you don't have to go through the extent of sending the big packet first and then it will be dropped and then you have to resend again. What happens here is even before you send out anything, there is what we call path MTU discovery. It will try to check the MTU size of the path. Okay, so every session this will be done. Let's say from router A to router B and router C, probably they set their MTU size to 1500. But from router C onwards, it was set to something smaller, let's say 1300. Okay, so with ICMP, okay, so ICMP v6 is the protocol that we use to do path MTU discovery. Okay, it will check the links Now, and when it sees that in router C, okay, it can only support 1300, okay, an ICMP packet too big will be received by router A, and then router A will now have to form his packets, okay, using that MTU size. If no reply or response was received by router A, it will assume, okay, that 1500, which is the MTU size set for router A, will be the size of the packets and send out that big size. Okay, so that's path MTU discovery. The good thing about that, again, is you don't have to send out packets first and then it will be dropped. This time, the MTU size is known even before you actually send out packets. Built-in features for multicast and anycast groups. Now, this one is pretty much also related to this last one, which means no more broadcast. Now, in IPv4, we use broadcast in a lot of things, okay? In finding out different machines within the LAN, we use broadcast, okay? So broadcast address plays a really huge part. Now, in IPv6, we disregard or we removed broadcast. Now, we're only using either anycast, multicast, and anycast groups. No more broadcast. Broadcast, while it is useful, it has also been used to, say, send out attacks and also adds a lot of noise in the network. And so when building up IPv6, they thought that it is not really a good thing, especially if you have a large network. Okay, it adds up to the traffic basically that is not useful for everyone. So they removed broadcast. It eliminates triangular routing and simplifies deployment of mobile IP-based system. Now this one is for mobile networking. So if you're a mobile operator, this is a good news for you because with this functionality, basically what we can see is before, normally we use triangular routing. So if you have, say, if I am with an operator and I'm in my home network, if I have to move somewhere else, let's say I'm going overseas, I'm going roaming. So when I send out messages, it always has to go back to my home network, okay, before it is sent out to the destination. So you can see it has to pass through 3 different nodes. So that's why it's called triangular routing. Now with IPv6, they want to do away with some of that complications and makes it possible for, say, a roaming node to actually connect to its destination or a correspondence node without having to go through the home node. So it's something that is really useful for them. It is still under a lot of changes, a lot of discussions in IETF, so you'll see a lot of changes in this in the near future. And the last one is it's got built-in support for IPsec, VPN, and QoS tagging. I think simply put, you can say that it has more security functionalities than IPv4. As I've said in the earlier slides, the way we used IPv6, the way we use the network has changed immensely compared to how we use it before. We use it in a lot of our personal transactions, paying banks, buying online, sending information that is very critical, let's say, for our company, and so it has to be protected. So with IPv6, IPsec is already built in. What is IPsec? IPsec is IP security. Now you may say that, hey, we already have IPsec in IPv4. Well, actually, IPsec was originally created to be part of IPv6. However, since it's taking a while for us to migrate into IPv6, so they thought of ways to port this IPsec into use so that it can be useful in an IPv4 setting. So in IPv4, IPsec is a totally independent protocol, okay, built on top of IPv4. It's in the same layer, but it's another application altogether. But in IPv6, it's built in with the protocol. So we can have end-to-end secure connections, let's say, between this laptop, this computer, onto any laptop around the world, and can have a secure connection, okay, using IPsec. It uses public and private key cryptographies and so it's really very secure. Now, so those are some of the functionalities. Any questions for this? Okay, so these are not just all, of course. If you look at the RFC, that's RFC 2460, you will see a lot of good things, new functionalities, new features involved with the V6. All right, any questions? I can see. Can I go over triangular routing again? All right. Let me just check whether I have that slide here. I normally don't include that in e-learning. Okay, so I don't have the slides, but basically what happens in normal triangular routing is, let's say when you send out messages, or say, there are terminologies included there. Say, I'm in my home network, that is my home node. Say I have to connect or communicate or send messages to, let's say, someone overseas. So that is my correspondence node. Okay, so I'm in my home node connecting to a correspondence node. That's a normal setup. Now what if I go somewhere else? In this case, you can think of, let's say, the normal phone operators. So I am subscribed to, let's say, in Australia, I'm subscribed to, let's say, Telstra. That's my mobile provider. Okay, so what if I have to go overseas? So in that case, we call it as roaming, right? So let's say I go to Singapore. In Singapore, there are other providers, okay? But they have agreements with, let's say, my provider, which is Telstra, so that I can still use my mobile phone in Singapore while I'm away. So what happens when I'm sending out data using mobile networks is I am in another remote node. I have to go through my home node to get to my correspondence node. Okay, so those are the three nodes. Now with normal operations, this is what we call binding updates. You have to do binding updates from your remote node to your home node first. Okay, so that's why we call it triangular routing. Now with IPv6, they were looking at being able to create binding updates from my remote node going to my correspondence node without having to always pass through my home node. Okay, maybe just set up one binding update with my home node. Once that's established, everything else, all communications, will be from my remote node going to the correspondence node, and it doesn't have to go through my home node. So in the gist, that's what we mean by those changes, and that is essentially what the difference between triangular routing and the mobile operations with IPv6. Is it clear enough, John? Hopefully I was able to answer your question. I'll go and find out. I couldn't remember the RFC for that on top of my head. Once I do, I'll write it down here. Now, let's look at different IPv6 addressing models. As I've said, we are no longer using broadcast. Okay, we don't need broadcast in IPv6, and we'll stick with just these three addressing models. Now, why is this important? Well, when you send out packets, you either send it out to just one node, which is your destination, or you can send it out to a group. In IPv4, we even go to the extent of sending out to everyone in our local network, right? In our broadcast domain. But essentially in V6, we only have three. These are unicast, anycast, and multicast. Now, when we say unicast, what does it mean? It's a packet that is sent from a single interface going to another single interface. So it's a one-to-one correspondence. You have one source address, one destination address. On the packet that is created on your source, let's say node, which in this case is this one, okay, the packet will contain a source address and one destination address, which is essentially just for one node at the other side of the network. When we say anycast and multicast, they are pretty much similar to each other. Now, both of them will send from one node going to a set of multiple interfaces or multiple nodes. Okay, now what's the difference between them? When you say multicast, it's like this. Here, going to all these three nodes that are belonging to the multicast group. So my destination now is a multicast address for a certain multicast group. So these three machines here all belong to the same multicast group. It's like, if I want to make an analogy, if I have to send out an email, say, to a mailing list. I'm a member of that mailing list. When I compose my email, okay, I only have to send one, and then it will be received by everyone that is part of the mailing list. Okay, so in this case, same with multicast, this machine here only has to generate one packet, and all of that will be replicated and sent out to everyone that's a member of your lists. Okay, so this is used mostly in streaming, say video conferencing type of usage. So it's pretty useful thing. We have multicast in IPv6. Now Anycast, on the other hand, is, as I've said, very similar to multicast, but the difference is when I send out the message from here, it will only be sent to one among the say all the nodes that belong to the same Anycast group. Okay, so here all these three are part of the same Anycast group. However, only the nearest one, or the closest interface, will be able to receive my message. In this case, it's just this machine. All right, how do we know which one is nearest? Well, it's pretty simple. It's just a matter of, let's say, computing routing distance. It is dependent on the routing protocol that is used when sending out these messages. Okay, so it depends on the different metrics. Maybe it's based on the number of hop counts, the bandwidth, all of those sort of things. So those are the three different IPv6 addressing models. Now let's look at the comparison between the protocol headers of IPv4 as compared with the protocol headers in IPv6. Now what can we see here? Now in IPv4 you can see a lot of fields. In IPv6 it looks bigger, but if you count the number of fields, it's actually a lot less than IPv4. So a few numbers, in IPv4 you have 10 basic header fields. In IPv6 we have 6. Okay, so that's already 4 less than what we have with IPv4. In IPv4, again, I've mentioned this earlier, it has 20 octets, 20 bytes of header in IPv4. In IPv6 we have 40, so that's double the number of octets, or the size, as in IPv4 headers. However, in IPv4 it is variable, so that's 20 bytes plus plus, so 20 bytes, but it can increase depending on the options that you add, okay, on your header. In IPv6, however, it is fixed size, so 40 octets all throughout. It will never change. So what's the difference, or what is the effect of that in routers? Now your router does not have to compute the size of the header, okay, in IPv6 anymore. Okay, so less better performance, less things to do for your routers, so it can send out millions and millions of packets to the network. Now let's look at the fields one by one. So some of the fields here have not changed at all, and it's the same as the one that you have in IPv6. Okay, so it's pretty much just copied from v4 to v6. What are those fields? Version, okay, version is still the same, that's 4 bits. So in IPv4, that should be 0100, okay? In IPv6, that should be 0110. So it stands for 4 in IPv4, 6 in IPv6, okay, in just binary. Now the source and destination addresses have not changed as well. Now the only difference here is in v6, you have more space to allow for 128 bits of source address, 128 bits of destination address. But other than that, the functions and everything are the same with v4 and v6. Okay, so those yellow ones, again, are fields that have been kept from v4 to v6. Now let's look at the fields that have been removed or have not been kept when we went to v6. So essentially, or this one, header lengths, identification, flags, fragmentation, offset. Why we don't have it? We don't have fragmentation, right? Header checksums. We don't need checksums in IPv6 because it's basically fixed size. Options. Now the options field is no longer there, so we can have a fixed size IPv6 header. However, we will be adding extension headers. Okay, so we removed options field. Okay, because even if, let's say, we don't need to add anything in IPv4, it's still there. You still have the options field. Your router still has to try to interpret what are the fields in your options field. Okay, so it will still compute that. However, in v6, we said that if we don't need something, then don't add it, don't include it on the basic headers. But if we need to add something, then we have the flexibility to do that, okay, by using extension headers. Okay, but basic header, it doesn't have that yet, but you can add extension headers. All right, so all of the ones in red have been removed from v4 and you cannot see them in the IPv6 header. All right, clear? I hope it's still clear as of this point. Now the ones in, say, I think that's kind of a light bluish green color. Now those are the fields that have somehow changed from v4 to v6, but essentially most functionalities are the same. So what are those? Type of service in IPv4 is now traffic class in IPv6. So these are, say, identifying the different types of packets that's passing through, assigning different classes to them, and assigning priorities. Total length in IPv4 is now payload length. When we say total length in v4, that's the combined header and payload size in v4. Now in IPv6, we've said that we don't need to compute the header size. It's fixed. It's 40 bytes. So we only need to compute the size of the payload this time. So just a change because we're not computing the entire thing anymore, just the payload. Okay. Now time to live has been replaced by hop limits. Now time to live is a function of basically of time. It's in milliseconds, nanoseconds even. So when you send out packets, it has a TTL, a lifetime. When that TTL expires, that packet will just be dropped from the network. Okay. However, time in itself is very relative. Even if you have, let's say, external time servers that can give, say, exact times to your machines or to your devices, you cannot be sure that they are 100% equivalent. Okay, they might vary by a few milliseconds from each other. So they said that because of this relative value, they decided to let go of TTLs, but instead use hop limits. So hop limits is a number of, it's a count, the number of hops or nodes that your packet has to go through to get to its destination. Okay, so this hop limit size is, I think, 8 bits. Okay, this field, so you can have up to 256 hops without your packet being dropped. Okay, so those are the things that have essentially been been changed a little, but works quite the same. The last thing here is flow label. What is flow label? Now this is a new field in IPv6. Now you can think of flow label as something like traffic class because you can assign, okay, different flows. So essentially, if you have different types of traffic, let's say you have something for streaming, you have something for voice, you have something from, let's say, text or email type of, or those that you access, let's say, websites. So different type of traffic, you assign different flows, and then you assign priority to them. Let's say voice messages are more important than normal UDP ones, of course. So you give priority to that, okay, over your network. So it's like having QoS or quality of service. But compared to traffic class, it has more granularity, okay, because you have more control of what flows will be assigned to your packets. In traffic class, these are predetermined types. Okay, so is this clear? Hopefully it is. John and Shahil, If you have questions about this slide, please do let me know. Otherwise, I'll just move forward to the next few slides. It's already 11:30. We started out late, so I hope it's okay if we extend, let's say, an extra 15 minutes more just to finish up these slides. We still have, I think, not too much, but probably around 6 or 7 more slides from here. Okay, any questions on the protocol header comparison? All right, let's go through the next slide, which is a bit of IPv6 addressing. Now, I have a more in-depth discussion of IPv6 addressing and subnetting in the next session, which starts at 12:30. But I'll just go through these quickly because this is something important, especially when you just new to IPv6. This is where you will find easily find the differences between v4 and v6 field. When you look at the IP addresses, you will see 128 bits instead of 32 bits. One more thing that you will see there is, oh, hey, we're not using dotted decimal anymore. In IPv4, the text representation for the IPv4 address uses the dotted decimal digits. So every octet, so your 32-bit address is divided into 4. Each of them is separated by a dot, okay? And each octet is now represented in decimal. So that's why we call it a dotted decimal format. So in IPv6, we're not using that anymore. We are instead using hexadecimal digits. So you have 128 bits, okay? And then use hex digits. So that will be, you'll have 32 hexadecimal digits in an IPv6 address. Now, we subdivide them into different fields. Each of the fields will have 16 bits. Okay, so when you use hex digit, that means you'll have 4 hexadecimal digits per field. And then each of these fields are now separated by a colon. So see the differences? We're not using decimals, we're using hex. We're not using dots, we're using colons. Okay, each field is not per octet anymore. Each field is now 16 bits each field. Alright, so as an example, this is an IPv6 address. It's a complete v6 address. If you count it all up, it will have how many fields? Should have 8 fields. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 fields, and each field is separated by a dot. There is a way in which you can abbreviate that, okay? So in this case, when you just first got your IPv6 address, it will have a lot of zeros, and then you can abbreviate that. Use double colons, such as in this case here, if you can see this one, or remove all the leading zeros. Okay, we'll look into that in more detail in another session. But essentially, I just want you to have a feel or have a look at what does an IPv6 address actually look, okay, which is this. If you have IPv6 enabled on your machines, go have a look. You will definitely have an IPv6 address which starts with FE80. That is an IPv6 address. Okay, now I think the more important part here is to look at the IPv6 addressing structure. So you have 128 bits. Now how do we subdivide that address? Or how do we actually give out those IPv6 addresses? Now, it's important to note that in an IPv6 address, you can pretty much divide it into 2 parts. One is this part here, up to here, from bit 1 to bit 64. That is called the network prefix. From bit 65 to bit 128, or essentially the second half of your IPv6 address, is called the interface ID. Now this is essential to know because the interface ID is used for assigning to single host. Okay, so each network, you can think of each VLAN, they will belong to the same network essentially, right? So they should have the same network prefix all the way up to the 64. Okay, so what I'm saying here is when you have one VLAN, okay, let's say in one room you have 10 machines. For those 10 machines, you will assign a single /64 IPv6 address range. Okay, so if you already have your IPv6 addresses, okay, let's start probably on this side so that it will be clearer. Now, when you want to deploy IPv6 on your networks, what's the first thing that you will do? If you are a service provider, you will go to either an RIR, so APNIC is a regional internet registry or RIR, or they can also go to their specific NIRs if they have them, or national internet registries. Okay, so if you are an ISP, a service provider, that's what you would do. Now, when you get your IPv6 block, you can either get a /32. That is the normal maximum. You can probably get a /48 if you are an end site. When we say end site, these are networks, let's say big organizations, universities, corporations, okay, governments perhaps. They can be considered as end sites. So they will get, most likely get a /48 IPv6 address block. Okay, now let's stick with ISP example. So your ISP will get a /32. When we say /32, that's 32 bits in the network prefix. Okay, so this is from bit 1 all the way to bit 31. Bit 0 all the way to bit 31 there. Okay, so from that /32, this ISP will use that to further subdelegate to, say, their customers. They can have smaller ISPs as their customers. You can have end site with their customers as well. So the recommendation, okay, is to assign either something from a /64 to an end site to a /48. So this gives an ISP an allowance to, say, get this and this range in between them. Okay, so from a single /32 IPv6 block, an ISP can now give, or can now have, to the power of 16 customers if they will give /48 for each of those customers. Okay, so now why do we say that the range should be from /64 to /48? Let's just say that this ISP has DSL customers, say home users. Is it necessary to give them a /48? Probably not. That might be too big for them. But the smallest that they can give them is a /64. Okay, again, we use a /64 to assign to a single subnet. Okay, however, say in the future, this home network requires more subnets, then they probably will request for bigger blocks, maybe a /63 or /62 block from the ISP. Okay, so you will only give a /64 if you think that that network will not grow. Say will have, let's say it's just very small, that there's no possibility of it having more than one subnet. Okay, if you have customers that are, let's say, medium sized, then it's up to you to decide at what range to put from here. Maybe a best common practice is to use a /56. 56 is somewhere in the middle here. Okay, somewhere in the middle of 48 and 64. And so this might be a better size for them. For big end user customers, then give /48. Now, having either /32 or /48 doesn't mean that you are only limited to that number. You can always request for more if you think that /32 is not big enough. So where do you request them? For ISPs, you request them from your say regional internet registry such as APNIC. Okay, and the normal maximum that you will get based on the current policies is a /32 IPv6 block. Any questions on this? Okay, a few about interface ID. Well, interface ID again is the lower 64 bits. Now there are different ways in which we can assign addresses to that. It can be using the HCP, it can be manually configured, but the most common way that we use is what we call the modified EUI64. So this one is based on the MAC address of your machine. Okay, so your machine has physical address, your MAC address, which is 48 bits. From there, it will be expanded into 48 bits by adding FFFE in the middle. Okay, and then modify the 7th bit so that it can be, let's say it can represent either it is unique address or a non-unique address. Okay, so that's essentially how you assign the last 64 bits. There is another way, which is to use an auto-generated pseudo-random numbers. A lot of operating systems are starting to use this now. When you say auto-generated, basically any address will be assigned to the last 64 bits. It's not depending on anything. It's not dependent on the MAC address itself. Why do we have that? This is called the privacy address. Let's say, because I am dependent on the MAC address, I'm using EUI64. Now, when I go to, say, a different country or a different network that provides a different network address. However, since my interface ID is generated from a physical address, which is based on my machine's MAC address, now it will always be the same wherever I go. So some people find it very, find it against their privacy, like if someone can keep track of where I'm going, whether I change networks, because they can easily find my interface ID. So because of that, they came up with this privacy addresses that uses random numbers. If you're using Windows-based machines, then it's usually using pseudo-random numbers. If you're using Mac, I think they've also started using that. Okay, you can always switch back and forth from EUI64 to random numbers if you want to. Now, we'll just wrap things up by looking at the global network prefix. This is important because, well, this is the IPv6 addresses that you will find on the internet. These are the routable addresses. So the range is 2000/3. So each of the 5 regional internet registries were able to get a /12 block out of that /3. So if you request your IP address from APNIC, normally your IPv6 address will fall under this 2400/12 IPv6 address block. Okay? This is just an illustration of the entire IPv6 address space, just to show you how huge the IPv6 address space is. So as I've said in the previous slide, you have /3, right? So /3 is the global unicast address space. Now from that /3, we have divided them into /12s. So these /12s we should have a total of 512 /12s in a /3. From that, 5 have already been used or given to the RIRs. 1 is used for any other purposes such as experimental and such. And so you can see that the IANA reserve, you subtract 512. From 512, you subtract 5 and another 1 for miscellaneous. So it leaves 506 /12s in IANA's pool at this point. Okay, once we run out of that 506 /12s, IANA can easily just tap another /3 from the IPv6 address space, and then same process, give /12s perhaps or bigger depending on our needs in the future, but essentially just give them again to the RIRs and then given to the LIRs or the ISPs and then given to end users. So that's how it works. Now, if you need an IPv6 address, go and check out our website, that's apnic.net. Now, if you already have an IPv4 address space, you can easily get IPv6. If you already have, let's say, an allocation, IPv4 allocation or assignment, if you log into my APNIC, there is a link there that essentially tells you to claim your IPv6 address. Okay, at no cost, you can get that. And it's automatically assigned to you. You don't need to provide any documentation or justifications. It will automatically be given to you. Okay, so that's how easy it is to get IPv6. We call this project the Kickstart IPv6 project or one-click policy. So basically, just log in, click the link on the main landing page, and you will have your IPv6 addresses. Okay, this is the current IPv6 BGP routing table. You can see when say BGP routing table, that's in the prefixes that are announced on the global internet. So those are the reachable networks. As of yesterday, I think, or the day before, it's at 13,489. Compared to IPv4, this is not enough. This is very little. However, what's good about this graph is you can see that from 2008 to 2010, you can see this a bit more exponential growth, and you can see from here to here that it has gone steeper, meaning we have more implementations, more deployments that has happened over the past 3 years. And that's a good thing for us, because when you started deploying IPv6, of course, there are other networks that are reachable from you now. Okay, so what I would suggest is, that is the end of our presentation. What I can suggest is attend the rest of the sessions. The next one is at 12:30. We will be covering IPv6 addressing and subnetting. So we'll give you more understanding of the different types of IPv6 addresses as well. And then at 2:30 we will be having IPv4 to IPv6 transition. So how will you go about the different techniques or technologies to transition from v4 to v6, or if you want to do dual stack, which is essentially running both v4 and v6, then you can also do that. So we'll have a look at those things in the next 2 modules. Hopefully you can join us there, so you'll have a complete understanding of at least the basic things that you need to know about IPv6, and then before you start your deployments. Now the login for that will be the same as your login for this one, so you don't have to re-register again. Just possibly just show up, and then we'll go through those slides. Now I'd like to ask everyone, some of you were just popping in and out. I think there might be some problems with the connectivity issues. I don't know from which end, but hopefully you got what you need from this session. If you need the slides, I would first encourage you to fill out the feedback form. So I'll put the feedback form in the chat, so it's here. So once you filled up the feedback form, you will be redirected to our FTP page, and you can download these slides in PDF format. So you can have a look at the materials again. If you have questions about them, you can easily shoot me an email, send me an email if some things are not clear to you. And then, you can probably start thinking about your own deployments. All right, thank you very much, everyone. I hope that you learned something from this class. Hopefully, we will see you again in the next e-learning.